Hello students, welcome to Engineering Mechanics Dynamics. My name is Dr. Hawk. I'll be preparing these videos and you are required to see the videos before you come to my class. So let's start. So today's learning objective is, at the end of the lecture, you should be able to describe the concept of position, displacement, velocity, and acceleration, and you'll be able to study particle motion along straight lines. We'll derive some formulas, and in next videos we'll solve problems. So what is dynamics? It is the branch of mechanics that deals with the accelerated motion of a body. Dynamics has two parts, kinematics and kinetics. Kinematics treats only the motion of an object and does not consider the force that causes the motion. For example, if I have a particle here, this particle, and it's moving along this direction, this x direction, and if I only consider the physical or geometrical position of the particle, for example, position, displacement, velocity, or acceleration, then then it is called kinematics. But if we do consider the force that is causing the motion, then we call it kinetics. So an easy way to start studying kinematics is to start with rectilinear kinematics. So rectilinear means straight path motion, straight path. So rectilinear kinematics is the analysis of motion of objects moving in a straight line path. So kinematics of an object can be characterized by specifying its position, displacement, velocity, and acceleration. Some fundamental concepts. So this we're gonna study what are these four things are. So position. Position specifies the location at any instant. It is a vector quantity, consists of magnitude and direction. So from now on, instead of an object, we'll assume a particle, because we're not considering the force acting on the body, so we'll assume the whole object as a particle. So for position, if we take this as a origin, the start point, and the location of my particle is here, which is s displacement, s distance away from the origin. So the position can be defined with s, and it also a vector quantity, because we also have to say it's located in s distance in this direction, for example x direction. Displacement, the change in position. So if my particle, which was here at the beginning, position 1, which has a position from origin was s, and after some time it was at position 2, so the change in position, this is displacement. So we can denote it by delta s, which could be s1 minus s. The unit for position and displacement, we can use meter, m, or feet, either one. So one thing we would like to clarify, the term displacement, sometimes it gets confused with the word distance. So what is the difference between displacement and distance? So let's see this example here. Assume the particle is at position A, which is this, and it traveled through this path, this curved path, and stopped at position B. So the distance traveled by the particle is the distance of this path. Actual displacement from location A to location B is only this distance here. So this one would be the displacement. Clear? So the next question we're gonna talk is can this position that we just talked about, position and displacement, be negative? Yes, it can be negative. So if we assume that anything beyond this origin, right side of the origin, is positive, then if my location is on the left side of the origin, it would be negative. So the next concept we're gonna talk about is velocity. So what is velocity? It is the rate of change of position with respect to time in a particular direction. So this also means that velocity is also a vector. It has a magnitude and direction. The magnitude of the velocity is also called the speed. So speed is not a vector, it's a scalar. Velocity also can be represented in two ways. One is instantaneous velocity. The second one is average velocity. So instantaneous velocity is the velocity of an instant, and average is the average of entire velocity. So from start to end point. So ds, the instantaneous velocity, is the small change in distance divided by the change happened during that small amount of time, dt. Average velocity is the total displacement, so final minus initial, so s final minus s initial divided by the change in time, so del t. There is interesting thing to should be clarified, and we'll solve the example to understand that. So let's solve this example. Let's say it's the distance traveled by the particle in the image here. So this is the particle, the start point. This is the traveling path. So the distance, which is this path traveled by this particle, is 100 meter. So the length, so the entire path is 100 meter. And it took 10 seconds to run this across this path. But the actual displacement, this from point A to point B, is only 10 meter. And the problem asks us to find the average velocity and average speed of the particle. So we know that the speed is the magnitude of velocity. So we may think that the velocity, the magnitude, the numerical value of the velocity and speed may be the same, but let's see. So the average velocity is the change in displacement, which is 10 meter, and the change in time is 10 second. So we got average velocity is 1 meter per second, and this is also the unit of velocity, meter per second. However, for the speed, we have to take the entire distance covered by the particle, so that is 100 meter, and divided by 10 seconds. So now it's 10 meter per second. So this is just to clarify that average velocity and average speed may not be the same. So now we're going to talk about acceleration. So acceleration is the rate of change of velocity with respect to time in a particular direction. So again, acceleration is a vector quantity that has a magnitude and a direction. Similar to velocity, acceleration also can be represented in two ways: instantaneous acceleration and average acceleration, and which is the dv over dt. And if we plug the value of v in derivative form from the previous slide, we'll get d square s over dt square. The average acceleration is easier, the change in velocity over the change of time, and you'll get the average velocity. So now let's also the unit of acceleration from this equation, we can see that the unit of velocity is meter per second, and then on the denominator you have dt, so it's second again. Finally, we got the unit is meter per second square, and this is the unit of acceleration. So to study the rectilinear kinematics, we can simplify this study by deriving 4 formulas. The formulas will help us to solve the problems, that's our goal, easily. And then we can derive this formula from the fundamental concepts that we just learned in previous slides. The 4 concept fundamental, for example, position, displacement, velocity, and acceleration. So from those definition, we can derive 4 formula, and it will help us to solve problem better and understand the problem better and solve easily. So the first formula is a first position function. So we'll start with before we derive this formula, we have to assume that the particle is under constant acceleration. So it's a continuous motion scenario, so no change happening in the motion, and during the entire time the acceleration was constant. What could be an example of constant acceleration? Gravitational pull, for example, this particle, or we can make it as a ball. If we let it go from any height h, it'll fall, and it's over time, but the acceleration is constant. That's g. We know it's 9.81 meter per second square. So this is an example of constant acceleration. So the formula that we're going to derive, the formula, it is only valid for if the acceleration is constant. So the first position function we want to derive is, we have to start from the average velocity definition. So we know that average velocity is the change in position, so final minus initial, on divided by the change in time. And we know that average can be found by summing up the final and initial divided by 2. So let's see, if we have a plot time on x direction and velocity in y direction, and this is 0, so there is 0 times 0 velocity. We're assuming that the initial velocity at time equals to 0 is u, and the final velocity at time t is v. And since we assumed constant acceleration, so the change will be linear from here to that. And the time is t. And if we take the slope, it's constant. So constant dv equals to dt. Acceleration, that is constant. Let's see. Constant. So now if we take the definition of average velocity, so the final velocity v minus, well, I will take average, so plus initial velocity, and to get an average we have to divide it by 2, and on this side we'll have the same thing, so delta s over delta t. So from here we can get our first formula, delta s. So change in displacement can be found if we know the initial and final velocity multiplied by delta t. So this is our first formula. If we know that the acceleration is constant, if we need to find any of this, or final velocity or initial velocity or time, we can use this formula. If we know the other part, we can find one from this equation. Let's move to the next slide. First, velocity function. So we're going to derive a velocity function by integrating the acceleration equation. We know, we assume that the acceleration is constant, so this doesn't change, and the instantaneous definition is dv over dt. So we'll take an integration of this equation. So dv over constant, so we can put the a outside and it'll be dt. The limit of the integration would be initial velocity u, final velocity v, initial time 0, final time t, and that would give us v u a, again for t, will have 0 to t. So that gives us the formula v minus u equals to a t acceleration multiplied by time, and it was normally written as v equals to u plus a t. So this is the second formula we derived, and we're gonna use that for solving problem. So let's do the next formula. This is the second position function, and we can derive it by integrating the velocity function we just derived here. So we're gonna start from this equation, and then we'll integrate this this formula. So if we integrate this equation, so by definition we replace the v with ds over dt. So we have now this equation, ds dt over dt equals to u plus at. So we'll get, for integration, ds equals to u dt plus a is constant, so we'll leave that out, t dt. If we do integration of this, we'll get s. So if we assume that so the upper and lower limit, I have not put that yet. So s initial at time equals to 0, and s final times 0. So at time equals to 0, the displacement was 0. The position was s naught. So t, and then 0 t. So we'll get s1 minus s naught equals to u t 0 t plus acceleration. So initial velocity u is constant, so it will not change over the integration. So now we have t here, so the integration would be t square over 2. So if we plug those values, we'll get s1 minus s naught equals to ut, because this one is 0, so, and half acceleration t square. We can also write it in this form: delta s equals to initial velocity multiplied by time plus half multiplied by acceleration into time whole square. So this is the third formula we just derived, and we're going to use it to solve problems. So the last formula we're going to derive is a second velocity function. So we're calling it a second velocity function. The first one, we called it first velocity function because it's a velocity formula. We can find the velocity if we know these terms. This one we're calling second position function because we derived one in the previous slide. So it's a position function, so we can find the position if we know these terms. Let me clarify that. Okay. ut is time plus half half at squared. Okay, so to derive the final formula out of the four, we have to use the definition of velocity and acceleration. So for instantaneous velocity, we know v equals to ds over dt. From this equation, we can say that dt is ds over v, and we can now we have to use the definition of acceleration. Acceleration equals to dv over dt. So now we're gonna plug this value here, and we'll get acceleration equals to dv over ds over v. That gives us an important relationship, that is we have to start from here to find our fourth formula. So if we do integration of this formula, we can get final velocity, initial velocity, v dv, and a is constant, acceleration is constant, so that's left out. Final initial ds. That gives us v squared over 2 final velocity v, initial velocity u, equals to acceleration and delta s, the change in s. If we simplify, we'll get v squared minus u squared, so final velocity square minus initial velocity square, equals to twice acceleration multiplied by change in distance. This can also be written as v squared equals to u squared plus twice acceleration delta s. So this is the final the fourth formula and final formula we derived, and we're going to use it for our problem solving. Okay, let's move to the next slide. So far we have studied and derived four formulas that we will use to solve problems if the problem is under constant acceleration. So the question comes, what if the motion is changing with time? And what do we mean by changing motion? Let me draw a graph explaining. This is for constant acceleration. Now, for the changing motion, an example could be, I'm driving a car. At the beginning, I started at a point u, that is my initial velocity, and I started to accelerate slowly, so my slope is shallow and low, and I'm accelerating very slowly up to a point time t1. Then I accelerated at a higher acceleration, but at constant acceleration. So higher rate but constant acceleration. So we have a different acceleration here than here, and I drive my car at that acceleration for a time t2. Then before, when I'm close to my destination, I slow down slowly, So my slope is again different. And finally I stopped here. And that was, for example, at time t3 I stopped. So that's my initial, that was my final. So you see from here to here, this time my acceleration was changing for every point. But from time t1 to t2, I had a constant acceleration, but that is different from the one I have here. For example, acceleration A, acceleration A1, acceleration A2, those are not the same. So this is not, acceleration is not constant. Here, when I'm slowing down, my slope is different for each of the points. So I have another scenario of acceleration 3. So I cannot use the formula that we just derived for constant acceleration. For this scenario, we have to use different formula or different approach. So one of the approach could be is that we solve time section by section. So we can solve the problem from t1 up to t1 time, and then we can solve the second part up to t2 time, assuming that t1 is the initial time and t2 is the final time, and then we can solve the third part assuming t2 time is the initial and t3 is the final, and we can add the cases together to get a solution. This is one approach, and we'll see more about changing motion when we do solve problem in next video. So the thing is that formula we derived assuming the constant acceleration is not valid here, and we have to use this approach. In summary, today we have learned the concept of position, displacement. We have studied velocity and acceleration. We got a definition of velocity. For instantaneous velocity, v over ds over dt, and average velocity is the change in distance over change in time. Same thing for acceleration, change in velocity over change in time, and it can also represent in this form, in a second derivative form. And average velocity is defined as delta v over delta t, and we derived 4 formulas, and that is only valid for constant acceleration. One is the first position formula. The second one is the first velocity formula. The third one is second position formula, and the fourth one is the final second velocity formula. So in our next video, we'll use these equations and this formula